Network deployment in rural areas is complicated by the varying degree of terrain that may be encountered when installing cables or fibers between cellular stations. Recently, the research community has also started investigating the feasibility of integrated access and backhaul (IAB), in which only a fraction of the base stations can connect to the traditional fiber-like infrastructure, while the other wirelessly rely on the backhaul traffic. Although long-term evolution (LTE) already support base stations with wireless backhaul, future integrated access and backhaul development foresee a more advanced and flexible solution with multi-hop communications, dynamic resource multiplexing, and a plug-and-play design for low-complexity deployments. 5G and new radio 5G introduces a new type of wireless backhaul known as integrated access and backhaul that is of a particular interest for dense deployment of street-level radio nodes. IAB, immediate access and backhaul, presents lower deployment costs and complexity compared to the traditional networks with fiber backhaul and facilitates the site installation even where fiber may not be available. For example, rural areas have a varying degree of terrain, making executing cable or fiber build out between cellular towers even more difficult and expensive. The massive data rate requirement of the new 6G access technologies may require further growth of backhaul capacity. Utilizing the THz terahertz, utilizing the THz band become quite important. Traditionally, the lack of high-power compact transmitters and high sensitivity receivers, combined with high propagation loss, propagation is the behavior of waves. So, combined with the high propagation loss, results from the much smaller wavelength at terahertz frequencies, limited the communication distance in the terahertz band. However, major advances in terahertz band devices technologies and physical layer techniques have recently made long-range terahertz communication a reality, not only for on-the-ground backhauls, but even for satellite communications. Also, many challenges accompany this spectrum, including the impact of atmospheric effects. It will be extremely important to design ad hoc scheduling procedures to efficiently split the resource between the access and the backhaul, and provide interference management, and to avoid worse network performance in crowded or heavy network traffic. Satellites and high-frequency solutions are currently applied in remote areas like sea, air, and deserts, and are likely to be the case in the future versions. Non-terrestrial network (NTN) systems include satellite systems at different orbits, high-altitude platforms, and balloons. Non-terrestrial network solutions may also serve other remote places by providing direct user access or backhaul connection, or complementing terrestrial services. Ultimately, we should look for hybrid or integrated terrestrial and non-terrestrial network solutions together. The benefits of non-terrestrial network includes communication resilience. Non-terrestrial platforms enable wide connectivity coverage and guarantee seamless service continuity. For example, in rural areas or when terrestrial infrastructure are not available, as in the case at the sea. 2. Energy-efficient connectivity. Non-terrestrial nodes can be deployed on demand, implementing smart duty cycle control mechanism, thereby reducing the operational and management costs of fixed infrastructure. 3. Resource optimization on parallel backhaul links. Non-terrestrial platforms offer an additional robust channel for backhauling operations, thereby saving terrestrial resources for access traffic requests. This also guarantees that on-the-ground terminals can find an alternate route to preserve the connection if terrestrial links are unavailable. 3. Quality of service enhancement through edge computing. Airborne stations or space, including satellites, can host mobile edge cloud functionalities to support communications, computing, and storage operations for on-the-ground users to execute their cloud services. 5. Communication on the move. Satellite provides high-speed connectivity to individuals in motion terminals that cannot benefit from terrestrial coverage, such as on planes or vessels. A disadvantage of existing satellite system is the high cost of both terminal and satellite connection. Future solutions should address these and provide economically affordable solutions. The integration of non-terrestrial network with mobile terrestrial systems has been initiated as a 3GPP study item. 3GPP is the third generation partnership project, which means it is a group of organization that give standards which develop protocols for mobile telecommunication. Let's go back. Where did we go? So, with the expectation of reducing costs with common chips, in addition to other benefits, after identification of the possible challenges, 3GPP has started to solve these problems. As the satellite system design's life cycle is rather long, it is anticipated that this 5G-based solution will be in use even early in 2030s. 6G should include the non-terrestrial component in its design from the outset to avoid expanding a lot of effort on this later. The constant optimization of appropriate protocol design still calls for long-term research to overcome the large propagation, coverage, high mobility, and enhance server quality and service continuity. From the implementation perspective, we need to maintain service continuity, which may in turn be very difficult to install, is also required. Moreover, to ensure the smooth commercial usage of the future integrated network, close cooperation among different operators with infrastructure sharing may also be needed. For example, core network construction by the terrestrial operator can be shared with a satellite-based access for user equipment located in different regions. A unified set of services can be provided with adjustment peer access based on radio access network capabilities, such as a mechanism with a specific gateway is feasible for the integration between terrestrial network and non-terrestrial network with either unified or different access techniques. Non-terrestrial network solutions, challenges, and research ideas. One, enabling the integration of the non-terrestrial and terrestrial includes enhancement of physical access and network layers, and that addresses new challenges like dealing with a significant end-to-end propagation delay, like satellite-friendly signals, like a low back-off signal that is friendly, they could mix together. To enable MEC, which is mobile edge computing, versus non-terrestrial network nodes. 3. Resource utilization, optimization, sharing, and hybrid system. How can we utilize the resources when we're doing a hybrid system between non-terrestrial and terrestrial networks? Excuse me. 2. Optimization of multi-layered networks. 3. From the implementation perspective, to enable the non-terrestrial network with efficient power amplifiers for satellites to boost their efficiency and improve link budget, and to enable the non-terrestrial network with efficient satellite platforms and its ability to overcome the difficulty of maintenance and reduce costs during the lifetime of satellite. And lastly, inexpensive non-terrestrial solutions should be in mind and affordable users.